shirt that's made.
This is the first shot with the 22 long rifle cartridge, and this is how you find out the muzzle kinetic energy and the velocity of a bullet that you don't know what it is. So in order to do this, after the bullet's been fired, you find theta from the camera. I couldn't find the height difference from the camera as the angle was kind of messed up, but I was able to do this in order to find H. So I took 46 centimeters, times it by cosine 40, and that gave me this side, which I subtracted from 46 centimeters to give me H. So H equals 11 centimeters, or 0.11 meters. And then you use the conservation of energy formula, and then you do all of this, and then you get down to the velocity of the bullet and the block right after impact. So the velocity of that entire unit is 1.468 meters a second. That's the velocity of the block and the bullet together. And then you can use the conservation of momentum to find out the velocity of the bullet itself. So we go down here, we plug all our numbers in, and we get the velocity of the bullet equals 368.78 meters a second, which is 1,209 feet per second, which is very, very close to what it actually is on the box. So on the box is saying about 1,280 to 1,300 feet per second. These are really high velocity rounds, but they're very, very small, as they only weigh 0.00233 kilograms, or 2.3 times 10 to the minus 3 kilograms. Very, very small, but moving very, very quickly. Now, we can convert this into kinetic energy by using the kinetic energy equation, which is EK equals mv squared over 2, or half mv squared. And there we get 158.5 kilogram meters a second, or joules. So this is very, very close to what the actual kinetic energy is. But it's still quite, it's still off. This is due to loss of energy either from air friction, because the target was 25 yards away from the gun, or it could be due to slack in the strings. When the pendulum tilted, it could have there could have been a little bit of a wiggle. I tried to minimize this with 4 strings, but it could have taken away energy there, and there's a lot of sound, and there's a lot of pieces flying from the wood. So this could all be contributing factors to why this number is lower than the actual number of joules. Okay, so this is the 12 gauge slug round. Now, as you can see, this bullet is a lot heavier than all the other rounds we fired, and the block is a lot heavier. In order to compensate for the bigger round and the bigger kinetic energy. So I couldn't find theta as it exceeded the limit of measure, and it hit the top, throwing the hammer into the air and a bunch of other stuff. Anyway, so there's a lot of energy wasted. As you can see, we found that the velocity of the bullet was 1,354 feet per second, but on the box it says it's 2,000 feet per second. So this can be lost due to air friction and the block hitting the top of the structure. And the kinetic energy of that bullet from the slower velocity is 1,656 joules. Now, this isn't right because this is less kinetic energy than the 270, but this should be a lot higher than the 270 because it's a way heavier bullet, almost double. So this is the kinetic energy found from this speed, the proper speed. So if we subtract the proper speed, or if we subtract the slower speed, the speed that was measured, from the proper speed, the 3,600 joules, we can get the amount of energy that was either wasted or expended on the structure and the air itself. So that's 1,955 joules of kinetic energy. So that's a lot of energy, and you think that that would do a lot more damage, but it really didn't because the wood bent and there was a lot of deformation inside of the block itself, like quite a bit. Like it really did some damage, and I'm even amazed that I hit that shot because I didn't even have a scope on the gun. So it kind of hit center, but there was still quite a bit of energy loss from the wiggle room in between the strings. So that's my physics ISU, and it was pretty fun filming and doing all of this.